Hello, everyone. Good afternoon to everyone watching this lecture that we are having. So, today's lecture has been organized by the Department of Physics, and the lecture is going to be chaired by Professor Tom Fearn from London. And his lecture is going to be on an introduction to NIR spectroscopy and its application to wood and wood products. So, first of all, I'd like to welcome Dr. Tom Fearn. Thank you so much for finding out time for this little lecture from you to all the students across the country of India. On the table, on the chair, we also have Dr. Shailja Pant, Principal, Dolphin PG Institute of Biomedical and Natural Sciences, Dehradun. And with me, I also have Dr. Ashish Raturi sir, who's the HOD of Department of Physics here at Dolphin PG Institute of Biomedical and Natural Sciences. So just to let everyone know, today after the session, we will also invite all the questions, all the doubts that you may have from Professor Tom Fern, and you can put that up on the comment section of your YouTube channel. And any doubts and queries will be answered in the end of the session. So I think we can start with the show. And the first thing that I'm going to do is I'm going to invite our principal ma'am, Dr. Shalja Pant, to introduce our guests to the event. Please, ma'am.
Thank you. Dear participants, students, and friends, welcome you to the distinguished lecture on an introduction to NIR spectroscopy and its application for the analysis of wood and wood products. On behalf of Dolphin PG Institute of Biomedical and Natural Sciences, Dehradun, I am pleased to welcome the eminent speaker of today's lecture, Professor Tom Fearn, a professor of applied statistics in the Department of Statistical Science at University College, London. Welcome you, sir.
Thank you.
I take the privilege to give a brief introduction about my institute. Dolphin PG Institute of Biomedical and Natural Sciences is affiliated by HNP Gadwal Central University, Srinagar, and it is recognized by UGC under Section 2F. The institute is accredited by NAC with a grade of B++, and Dolphin PG Institute, it offers job-oriented undergraduate and postgraduate programs in the field of life sciences and biomedical sciences, education, and commerce. Institute time to time organizes seminars, conferences, workshops, scientific talks, and distinguished lectures so that our students get exposure to the latest in science and technology and the basic concepts of science. And today's lecture is another step towards the same mission. As we were discussing, NIR spectroscopy has made a marked progress in many aspects, right from instrumentation to spectral analysis, and has a wide application, not only in chemical aspects like physical chemistry, inorganic matter, in polymer science, process analysis, in food engineering, pharmaceuticals, biomedical, imaging, and many more. So I'm sure it is going to be a very interesting session for one and all, and the students, I guess, will develop a curiosity to further explore the other possible application of spectroscopy. Once again, I welcome Professor Tom Fearn for this distinguished lecture. Welcome you, sir.
Thank you.
Thank you so much, ma'am, for the wonderful words. Now, I would like to invite Ashish Raturi, sir, to speak a few sentences on today's event. Please, sir.
Thank you, Shantanu. And once again, good afternoon, good morning, everyone, as per your time zone. On behalf of Dolphin PG Institute of Biomedical and Natural Sciences, Dehradun, and on my own behalf, I, Dr. Ashish Raturi, welcome you all. And really, it's a delightful to have all you here today attend this very distinguished lecture. Dear friends, it's my privilege to introduce today's speaker. Dear participants, as you know, the Department of Physics of Dolphin Institute always brings to you the intellectuals from across the globe for enriching our students, researchers, and faculty's knowledge base in several ways. And in this continuation, today we have a very distinguished personality from the intellectual domain of globe. He is none other than Professor Tom Fearn. He is a professor of applied statistics, Department of Statistical Science at University College London. He was previously head of the department from 2002 to 2007, and again from 2011 to 2016. He has BA in mathematics from Oxford, an MSc in statistics from Imperial College, and a PhD in statistics from University College, London. Before joining the statistics department at UCL in 1989, he worked for 11 years at Flour Milling and Banking Research Association at Cornell. Professor Tom has a general interest in applied statistics and has worked on application in many areas, including food and agriculture, analytic chemistry, and medicine. He has a particular interest in NIR spectroscopy and the chemometric methodology that has been developed to deal with high dimensional data that arises from this and similar applications. Dear friends, I cannot summarize his broad spectrum in very few words. Really, he is a living legend in the field of chemometric analysis and foremost statistician in the scientific community. Dear participants, one thing I want to recapitulate when I was in early days of my research, and I was wondering that how the NIR spectroscopy can evaluate the mechanical property, because we are evaluating the mechanical properties of wood species generally in a destructive way. And you will be surprised that he was the Professor Tom Fearn who indirectly helped me. And I can say he's unofficial, but personally, he played a role as a co-supervisor for me for pursuing my PhD program. Really, he is a truly scientific intuition and has made him as a constant oasis of ideas and passion in near infrared spectroscopy, which exponentially inspired and enriched my growth during my early research days. Thank you, sir, for helping me in this particular program. Despite being very occupied, he accepted our invitation, shows his strong commitment for academia. So, without any further ado, I would like to invite Professor Tom Fearn to deliver his talk on Introduction to NIR Spectroscopy and its application to analysis of wood and wood products. Thank you. Now, sir, mic is over to you.
Okay, thank you, Ashish. It's going to be hard to live up to those introductions, but I'll try. And it's a real pleasure to be here today. So can we share the screen?
Yes.
Thank you very much. So there's my title and there's my affiliation, and there's an email there. If people have questions on reflection, you're welcome to email me. I don't promise to have an answer, but I'll try. So let's see if this works. Okay, so here's an overview of what I'm going to talk about. I'm going to talk about a lot of things and in not much time, so it's going to be quite superficial in some places. I'm also going to assume that you don't know much about any of this, so I'm going to spend some time, I'm sure, telling people things they know. I hope I'll tell everybody something they don't know. But if I bore you with things you know, then sorry, but I'm having to sort of assume that because people are from a wide variety of backgrounds, they may not know almost anything. So I'm going to talk a bit about where I'm coming from, a bit about the underlying ideas of NIR spectroscopy, show you a couple of pictures of instruments, talk about the calibration, which is really the area I'm most familiar with, and then a bit about applications, including something about wood, but that will be, like most of it, fairly superficial. But anyway, let's get going. So where I'm coming from, I'm a statistician by training. In 1978, I went to an outfit called the Flour Milling and Baking Research Association, where they were working with near-infrared to measure things like moisture and protein in wheat and wheat flour. And I started working with those instruments then, and I've carried on working with them in various applications, but mainly, but not entirely, food analysis, just because that's where my contacts are. I'm going to talk about the whole spread of NIR spectroscopy, and that means I'm going to have to talk about physics. And I'm not a physicist. I'm acutely aware that there may be people in the audience who know a lot more physics than I do. So apologies perhaps for my simplifications. And if I get anything horrendously wrong, I hope people will tell me in the chat or ask afterwards. So for quite a bit of this, I'm on the boundaries of my comfort zone, I think, but we'll see. So let's start with vibrational spectroscopy, which is what NIR is one example of. And what's going on underneath it all is vibrations between the atoms in molecules. So the picture, which I hope you can just about read if the slide's big enough on your screen, the picture shows a very simple molecule which has got 3 atoms. So it's got it's labeled AX2. That's one of the atoms is A and the other 2 are X. So the one in the middle is the cursor visible? Give me a nod, Ashish, if you can see the cursor.
Yes, sir.
No.
Cursor is not visible, sir.
Not visible. Okay, so never mind. I won't use it. So if you look at the first of the pictures, the top left, the atom in the center is the A, and the 2 above it are both X's. And the obvious example of this would be water. 2 hydrogens up at the top and an oxygen in the middle there. And that triple of atoms can vibrate in lots of different ways. And it's only 3 atoms there. But you can have symmetrical stretching. And if I were in a lecture room, what you do now is you stick your arms up and you do this for the symmetrical stretching. And the asymmetrical stretching is like that. And the in-plane deformation is that, and the out of plane is okay. So you get the idea. There are at least half a dozen different ways that even 3 atoms can vibrate when they're joined together in a molecule. And those molecular bonds can absorb energy. So they absorb energy from a photon, and that makes them vibrate more. But because of all the rules of quantum physics, which is somewhere where I'm way out of my comfort zone, they can only absorb energy from a photon that has exactly the right energy. It's like a resonant frequency. It's like you have the right energy, which means the right frequency, and this bond will absorb and will increase its vibration. So what we're measuring when we do spectroscopy, vibrational spectroscopy, is the absorption of photons, or the absorption of energy from photons by molecular bonds. You can see that even this very simple molecule, water, for example, will have several modes of vibration. And each one of those will have a different energy, a different frequency at which it absorbs. And so there are multiple frequencies there just for one simple molecule. And also there are things that are like harmonics in music. The bonds can absorb at approximately, not exactly because of some anharmonicity and things, at approximately 2 and 3 times the fundamental frequencies. So it can take the base level of energy or 2 or 3 times roughly. And those absorptions are called overturns. To complicate it even more, it's possible for 2 of the different vibrations to share the energy from one photon. So that means that photons with a higher energy level, a higher frequency, can share that energy between two different vibrations, and those are called combination bands. So when you add together the various fundamental frequencies, the various overtones, and the various combination bands, you get quite a lot of absorbances just from this simple molecule. And you can imagine how many you get from a quite complicated organic molecule with lots of atoms in there and lots of bonds. So that's what's going on approximately at a sort of fundamental level. Why are we interested in the near infrared as a place to measure things? Well, here's my crude drawing of the electromagnetic spectrum, or at least a little part of it. So it includes lots and lots of different types of electromagnetic radiation. The bit we're most familiar with is the visible bit. So this picture here is labeled in nanometers, which is meters times 10 to the minus 9, which is what the units that are typically used for near infrared, although not exclusively, and that they're wavelengths. And the bit what we can see, the visible light, is between approximately 400 and 750 nanometers. So at the 400 end, it's blue, violet, and then as you get to shorter wavelengths, you get into the ultraviolet, which we can't see, and then X-ray. On the other end, 750 is red. After you go past the red, you get into the near infrared. That's the short wavelength end of the infrared. And you can't see that, but you can feel it. So if you put your hands up to a fire, you can see the red glow, but most of what you can feel is longer wavelengths, which are carrying energy out to you. And then we go into the mid-infrared and past that, far infrared, radio, etc. The fundamental vibrational absorptions that I've been talking about happen in the mid-infrared. So they happen in the box to the right of the near infrared. And notice the boxes aren't to scale, so certainly not in terms of wavelength. They're all the same size and they cover very, very different wavelength ranges. The reason, what happens with these vibrational absorptions is that although the fundamental ones are in the mid-infrared, the overtones and combination bands occur in the near-infrared. And so we can see not the fundamentals, but the overtones, combination bands when we look at the near-infrared spectrum. And some of those are really quite strong, and in particular, the ones that we are of most interest when we do near-infrared spectroscopy are ones involving hydrogen as one of the atoms. And the NIR bands, the overtones and combination bands, are particularly strong when one of the atoms is hydrogen. And that's because hydrogen is very light. And so when you stick some energy in, it vibrates a lot, it vibrates a long way. And one of the consequences of that is that the overtones are quite strong. So the near-infrared region is a good region to look at absorptions that involve hydrogen, that involve a hydrogen bond. And so NH, nitrogen, hydrogen, CH, carbon, hydrogen, OH, oxygen, hydrogen, show really strong overtones, combination bands in the near-infrared. And they're interesting because basically they come from the sort of molecules that you see in life. They're organic molecules. They're the OH bonds you see in water, which is really important for life. But they're in hydrocarbons, they're in proteins, they're in starches, they're in sugars. And so if you want to look at biological materials, foodstuffs, agricultural stuffs, lots human bodies, lots of other things that are have got lots of organic molecules in. NIR is a good region to look. So one comment on this, on the arrows on that picture. So wavelength increases as you go left to right, but frequency, which is 1 over wavelength, increases as you go right to left. And the amount of energy in a photon increases with its frequency. So as you go across to the left to shorter wavelengths, you get more energy in the photons. As you go across to the right, the energy is weaker. And that has some benefits for using near infrared, so which I think are explained on the next slide. So the reason one's interested in using NIR rather than mid-IR is that because the photons that we are essentially whose energy levels we're looking at in NIR have more energy, they will penetrate further into a sample. So mid-IR will not go very far into anything. NIR will not go a whole long way into anything. We're still talking millimeters, maybe centimeter, but not enormous depths. But it will go into intact samples, and it won't all be absorbed because the absorptions are weaker. That it won't all be absorbed by the sample, even if the sample's got water in it. And that's the water is one important reason for the interest of NIR. If you want to use mid-IR and look at the fundamentals, then you have to dry samples basically, because otherwise the water will absorb just about everything that you put in, and you just won't see anything back. So looking at NIR enables you to look at samples that have got water in, wood being one example. That's got quite high water levels. And you wouldn't be able to use mid-IR on it without drying the samples out. There's a sort of secondary reason, which is that it's actually cheaper to make NIR instruments than mid-IR. So the optics are cheaper. Silica glass is transparent to NIR, but it will absorb mid-IR. So you have to go to quartz for mid-IR. And the source is a tungsten filament bulb is a perfectly good source of NIR radiation. You probably need something more specialized for mid-IR. The detectors are simpler. Everything gets a bit simpler because in the near-infrared region. So it's cheaper and easier to build the instrument. That doesn't mean you can't use mid-IR instruments. So some NIR instruments are actually Fourier transform mid-IR instruments who've had their range extended down to work in the NIR, but you can also build relatively cheap instruments as well, and that's another reason, although less important than the fact that you can measure intact samples and you can measure wet samples with NIR. So let me show you a few of the very, very many instruments that are available. So this is a typical bench instruments. So chemistry labs used to be really interesting. You could wander around them. There's lots of glass and tubing and things bubbling away. And now if you walk around a chemistry lab, it's just a load of boxes. And almost the only thing that distinguishes them is that different manufacturers tend to use different colors for their boxes. But they all look really pretty boring. And here's a pretty boring looking instrument. It's a filter instrument. It's quite old, probably dates back to the 1990s. And that uses interference filters to select particular regions of the NIR. I think it's probably got 19 filters in, so it will select 19 different, not quite wavelengths, because the interference filters don't pick out a wavelength, they pick out a narrow band of wavelengths. And there's a rotating wheel in there with the filters on, and it measures with each filter in turn. And the way you put the sample into that one is it's the little white circular cup that's on a drawer. And this is probably wheat flour, which you put into a cup, and then you push the drawer into the instrument, and it shines NIR radiation at different wavelengths on there. And then what's measured is what's reflected, what comes back from the sample. So the light goes in, it bounces around inside this powdered sample, and some of it is absorbed and some of it comes out. And what's measured there is what comes out, and it's called reflectance. So Some others will actually transmit light through samples. You wouldn't do it with this type of sample, i.e. A cupful of flour, because not enough would get through. But you can transmit through some samples, and some instruments work with transmission, and some instruments will work with either reflectance or transmittance. So that's a quite old instrument. It's got interference filters in. There are very similar looking boxes. In fact, I think there's an identical looking box, or was, that had what's called a monochromator in, which is a ruled grid which acts like a prism and will enable you to measure the whole spectrum over the whole NIR range. The box looks the same. What you get out is a lot more data. Oops. So the interesting recent developments are the appearance on the market of quite a lot of portable instruments. So those big boxes, and there are lots and lots of different sorts of big boxes, measuring over different ranges, measuring using different techniques. Some of them use Fourier transform spectroscopy. They've been around since the end of the 70s. Although they've developed a lot since then. They're much better instruments now than they were then. But what's interesting now is that there are a lot of portable instruments on the market. And there's a picture of one of them top right. And that's called a micro NIR. It's or micro NIR, I forget. It's by a company called VRV, who I've got no particular axe to grind for. I just chose that one because I've actually been involved in research that has used it, so I know it works. It measures a spectrum from 900 to 1700 nanometers, which is a bit of a restriction because it misses out some of the interesting stuff between 1700 and 2500. But it's very portable. The spectrophotometer, the instrument, is very small. It's only the bit beyond the purple button. The bit the person's holding is just the handle, basically. So only a tiny bit of it is the spectrophotometer. It's very small indeed. And it's exciting because it means you don't have to take the sample into the lab anymore. You can take the lab to the sample. You can take the instrument to the sample. And you can literally use it in the field. You can use it in a field to measure crops. It's got drawbacks. You don't get anything for nothing. It's a much smaller instrument, so typically with these instruments, the spectral range is a lot more limited. The spectra are not such high quality as they are in a big box that sits on a lab bench, partly because the box sitting on the lab bench is in fairly well-controlled environment, whereas if you take this out into the field, it's going to be working in lots of different temperatures and humidities, and it's going to have to cope with those. So the spectra are not as good. Some of them, not this one, have problems with stability because there's a lot of temperature sensitivity around, and it's hard to control the temperature of the detector, for example. But many of them are really serious instruments, and they've got lots of potential applications. And people are beginning to see some really credible applications for instruments like this. And there's an enormous potential. There are lots and lots of things one might use it for, wood being one of them, I imagine. So I've talked about the advantages of near-infrared spectroscopy. Here's the big disadvantage. The spectra look incredibly messy. So here are some spectra, not of wood, but of biscuit doughs. And the reason they're biscuit doughs is because I've got spectra of lots of food things, and I don't personally have any spectra of wood, and to show some I'd have to ask somebody's permission, and it's easier just to use some of mine. So spectra of wood look remarkably similar, in fact, and that's maybe not surprising because it's wood, it's water and starch, and in the case of the biscuits, protein and sugars, which look a lot like cellulose, which are causing the peaks in here. There are a lot of peaks. There are a lot more than you think there are. This isn't just 20 overlapping peaks, it's hundreds of overlapping peaks, because we've got overtones and combination bands from lots of really quite complicated molecules in here. And also some of the peaks get spread out a bit by something called hydrogen bonding, which shifts the peaks a bit. But this carries lots of information about the composition of the biscuit doughs, about the amount of water, sugars, protein, oil in the biscuit doughs. But extracting it is quite messy. What you can't do is take one single wavelength and say this corresponds to an absorption. Oh yeah, I should explain the vertical scale. It's log 1 over r, so it's the log of 1 over reflectance. Reflectance being the what comes back, the proportion of incident light that comes back. And the reason, and that's called absorbance. And the reason it's used is because of something called Beer's law, which doesn't apply here, but does apply in other situations. So if you were doing transmission through a dilute solution, then there would be a linear relation between concentration of what you're looking at and log 1 over t. And because of that, people use log 1 over r, and it's called absorbance. It's the standard thing to use. So this carries lots of information, but extracting it's difficult. If you just take one wavelength and plot the absorbance at that wavelength against moisture content or protein content, you will not get a good linear relationship. And that's for two reasons. One is there are lots of peaks and they all overlap, so everything's interfering with everything else. And the vertical movement that you're seeing, these sort of almost parallel but not quite movement in all these spectra, is not to do with the chemistry, it's to do with the physics. It's to do with how much light's coming back overall, and that's to do with the physical composition of these biscuit doughs. It's a bit to do with the surface texture and color. It's also probably a bit to do with the density inside. But that vertical shift isn't telling you much about the chemistry. It's getting in the way. And because of those two things, one has to use multiple wavelengths to get equations, to get algorithms that will predict the composition of the doughs. And that's the big disadvantage. It means you have to involve people like me in order to get calibrations. Well, you don't because there's perfectly good software that will do it, but you have to involve techniques from what's called chemometrics, which is multivariate calibration using lots of wavelengths in this context. And that's a drawback in some ways. It also, the other drawback is it can be harder to justify why the thing's working. It's harder to assign particular absorbances to particular bonds when you're coming to overtones and combination bands, partly because there are so many and partly because some of them are very close to each other. And so calibration and interpretation is harder, and that's the big drawback. But it is worth struggling with those because of the opportunities. So the standard calibration procedure looks like this. You take some samples and you measure, so maybe there are 50 samples there, maybe 100 samples, and you measure Y, which are the lab reference values. So you need to teach the system, teach some algorithm how to predict what you're interested in, the amount of cellulose in a sample of wood, the amount of water in a biscuit dough, to predict that from the spectral measurements. So you take a set of samples called a training set, you measure using the lab method the thing you're interested in, and you measure using the instrument a spectrum or some spectral data for each one of those samples. And then what you're going to do is use some algorithm, and I'll talk a little bit about the sort of algorithms one might use that establish a prediction rule that works well for these training samples. So you get some rule, some function of the spectral data that predicts the lab reference data. And that rule can be very simple. It can be just a linear combination of the spectral variables. So you predict Y, you predict the reference value from a constant plus a slope times absorbance at one wavelength plus another slope times absorbance at another wavelength, and so on. So just a linear combination of the spectral data. But obviously you can use much more complicated things. But in general, you need some algorithm that you can train to predict the training samples. And then it's really quite important to test the prediction rule on some samples that weren't used to train the algorithm. And that's because there's typically a lot of spectral data, and it's all too easy to do something called overfitting, which is to come up with a rule, and prediction rule, that works beautifully well for your training data and then doesn't extrapolate to any other data, because it's modeled not only the signal in the data, but it's modeling the noise as well. It's working too well. So it's really important to keep some samples aside, or even better, go out after you've finished and get some more samples and test the rule that you've just developed. And if it works on those, then you might be reasonably confident that it's going to work on other samples. The other comment here, which I could talk for a long time about, but I won't, is that the choice of training set's very important. So you can obviously, the problem the NIR has is identifying the information about the thing you're interested in against a background of lots of information about lots of other things that are interfering. So the brilliant thing about NIR spectra is that they carry lots of information. They carry information about the whole composition and some of the physical properties of the sample. But that means that you really have to be able to disentangle that from all the other properties that you're not interested in. And so you need a training set where not only there's variability in the thing you're interested in represented, but also variability in all the things that might interfere with it. So to take an obvious example, if you're trying to train your system to predict the protein in flower samples, then what you don't want to do is to train it on flower samples that have all got exactly 14% moisture content, because then you risk getting a prediction rule that only works for samples with 14% moisture content. And when it gets out into the real world and sees samples with varying moisture content, it won't work because it's never seen those before. So the training set has to represent the things that the future samples that you're going to want to predict. And that's sometimes quite hard. But what you should not do is make it too easy for yourself by selecting a very restricted training set, all carefully equilibrated to, all carefully chosen so they're very similar in lots of ways and all carefully equilibrated to the same moisture content and so on. You'll get some lovely training results and your calibration will be useless. So just a warning there. So what comes next? So a bit about the calibration procedure. It's very common to do something called a pre-treatment on your spectra. And that's because often some of the variability that's in there, and often the most of the variability that's in there is irrelevant to what you're trying to measure. So here are some spectra of wheat samples. Their transmission through glass vials that contain whole wheat grains. They're in the very short wave end of the near infrared. So it's only 850 to 1050. And that's because there's more energy there. So more radiation will get through, which you need when you're doing transmission. Those spectra look pretty boring. And most of the variability in them is just them moving up and down. And that's mainly due to the packing density of the wheat grains in the glass vials. You can get rid of a lot of that variability and make the spectra look more interesting by doing some pre-treatment. And I won't go into the details, but the one on the right is pre-treated by taking second derivatives. So that would be like the mathematical second derivative of these curves. It's the curvature at any point, or if you prefer, the slope of the slope at any point. And that takes out quite a lot of the vertical shifts, but also it's then corrected by something called a multiplicative, a single, it's called standard normal variate. It centers and scales the spectra to take out even more of the vertical shifts and the scaling. And you end up with the spectra on the right, where you can actually see there's a really interesting band at about 970 nanometers, and that's the water in the samples. And you can't see that in the original spectra. And because you can see it, the algorithms can see it as well. And so it'd be much easier for them to extract that information. There's also information on proteins and oils, but they're much smaller peaks. There are some around about just above 1,000 nanometers where there's some spreading out of the spectra. So it's often good to do pre-treatments to take out some of the unwanted variability. But then after that, what you need is some sort of algorithm that's going to give you a prediction equation. And when we used to work with, back in when I started in 78, the instruments had 6 filters in. And so the shape of the data, the spectral data matrix X, was like the one at the top. It was longer than it was wide, i.e. there were more samples in the training set than there were wavelengths to work with. And that meant you could use something called multiple linear regression, which fits a linear prediction equation. And that worked perfectly well until the manufacturers started putting a lot more filters in their instruments, and then started putting monochromators in and giving us an X that's the shape of the bottom picture, i.e. you've got maybe 100 samples, but you've got 700 wavelengths. And then you have an embarrassment of far too much spectral data. And you cannot use multiple regression with this. And that's because it would be, when you've got more variables than observations, more variables than samples, it's a bit like putting a straight line through 2 data points. It's a bit worse than that. It's putting a plane through 2 data points. You can put lots of planes through 2 data points. So you will be able, just because of the amount of data, to get equations from your algorithm that perfectly predict the training samples, but they'll never predict anything else. That they predict just because for any 2 points you can put a straight line, and there doesn't have to be any relationship between y and x. You can always put a straight line through there, but the chance that it will predict another y from another x is very, very small. So we have to look for, when we've got high dimensional spectra, we have to look for ways of coping with that and not overfitting, not using the amount of spectral data we've got to unreasonably predict the things that we want to predict. And there are various ways of there are lots of ways of doing that, but 2 common ways are 2 almost old-fashioned ways now, but they work very well, are to either chuck away most of the data. So you've got maybe 700 spectral variables from your instrument. Most calibration will work with a few wavelengths, and you can use various ways to select a few. And that's what we used to do when the first commercial monochromators came out. We would chuck away most of the data. And you can partly do that through physical chemical knowledge. You know that particular wavelengths have absorbances that are crucial for your application, and select those. You can use algorithms that will select wavelengths that work well. A different method, which is sort of become the standard because it's actually easier, is to use methods that construct factors from the spectral data. So instead of chucking most of it away, what you do is use some method, and principal components analysis is one of those, to construct new factors with new variables, which are linear combinations of the old ones, where a small number of the new variables will explain most of the variability in the spectrum. and then what you do is multiple regression, regressing y on the new variables, the much smaller number of new variables. One way to do that is something called PCR, principal components regression, and that just takes the spectral data and reduces its dimension without looking at y, without asking what you're going to predict. So it's an unsupervised learning method for constructing new spectral variables. What's much more common these days, because it works better basically, is something called partial least squares, which also looks at the y when it's constructing the x. So it constructs factors which both explain a lot of spectral variability, but also are going to be useful for predicting y. It's a sort of compromise between principal components and multiple regression. It constructs factors which explain x, but also explain y. And PLS is one of the standard ways to do these calibrations. It works really well in lots and lots of applications. And the reason it's used so much is that there's lots of very good software. And that software provides you with a lot of really useful diagnostic plots. So you get out pictures that look like spectra, and therefore you can interpret those. Even with these methods, even reducing the dimension, there's still a risk of overfitting, and it is really still important to test what you end up with on some unseen samples. So do whatever you like to get the algorithm, to get an equation, but please test it on some unseen samples before you rush into print and announce that you've got a wonderful method here. So let me talk in what time remains, a bit about applications. So the ones I'm most familiar with, and indeed the ones that really launched near infrared as quantitative spectroscopy, were in food and agriculture. And that's because it's really good at measuring moisture, protein, fat, sugars, and it will do it in intact or minimally pre-processed foodstuffs with minimal sample preparation. And it's used for lots of natural foodstuffs. It's wheat, for example, is traded on near-infrared measurements of moisture and protein, and has been for a long time. And that was that, along with similar measurements in flour, were the applications that really launched the commercial spectrometers, because there was a big market in the food and ag industries for that. It's now used for lots of other things. It's used for measuring those sorts of things in lots of foodstuffs, both raw materials and processed foodstuffs. It's used for lots of authenticity checks as well. So there's quite a lot of cheating goes on with when you have high-level food products, and it's possible to do quite a lot by way of checking authenticity using near-infrared. So lots of applications there, and they sort of drove the expansion of the commercial market in these machines. Pharma use it quite a bit. It's used for ingredient identity checks. Lots of pharma ingredients just look like white powders. If you get 2 barrels of white powder mixed up, you're in deep trouble. So there's lots of checking goes on, and there are NIR instruments which are designed usually with an optical probe. So you stick the fiber optic probe in the barrel of material, and it will do an identity check comparing the spectrum of that material with some standard spectra. So pharma ingredients have particularly sharp spectra because they're particularly simple, and so you can do that quite well. You can measure API, the content of the active ingredient in tablets as well. And an interesting application is following blending processes. So a lot of pharmaceutical tablets are made by blending various powders in a rotating drum. And you can actually use NIR to measure the extent to which the blending is complete and when to stop the process. And that's another important application. These are just some of the applications. It's used in environment. People use it in soil analysis. People use it in animal nutrition. I've worked with people using near infrared on eucalyptus leaves to measure their suitability for as food for koalas, and to try and get an idea of why koala populations are expanding in some places and shrinking in others. Australian colleagues, obviously, and again, lots and lots of other applications there, and applications in petrochemicals. Clearly, hydrocarbons have lots of lovely NIR absorbances. In medicine, both for, I guess, largely for diagnostic purposes. One can look at tissue samples and one can tell things about the tissue samples using NIR. The standard oxygen meter that people use get stuck on your finger if you go into hospital uses NIR. In fact, it's NIR transmission through the finger, and it's measuring oxygen in the blood, and lots more, which there's not time to list. I imagine many of you may have come across applications in different areas. I'll leave myself time to talk a bit about applications in wood, which I know Ashish is particularly interested in, and I think some of the rest of you may well be interested in too. The big plus, I think, for using NIR Spectra on wood is that it works on wet samples, and most wood is pretty wet. Well, not soaking wet, but IR wouldn't work on it unless you dried it out a lot. The drawback, I think, is that the penetration depth is only of the order of millimeters in something like wood. And so you're not going to be able to take one of these portable instruments, go out into a forest and point it at trees. It's not going to work. You're going to see a little bit of the bark. So most of the applications in the literature involve very carefully prepared cores or discs, and sectioned and prepared and examined by spectroscopy. The easiest thing to measure is moisture, because the absorbances are very big and very, very strong peaks. But after that, you can measure chemical composition, you can measure lignin, cellulose, hemicellulose relatively easily. It's much less obvious how you can measure physical properties like density or strength. Density a bit, because the sort of overall level of what you get back will depend on the density. But they have to... But there are quite a lot of successful calibrations for these sort of properties in the literature. They tend, I would guess, to rely on correlations with the chemical content most of the time. And those correlations can be quite strong, and they can enable you to get a reasonable prediction of things like density and strength. But it's much harder to explain what's going on. And because a lot of the applications rely on extrapolation, essentially, you're not measuring very deeply, and you may be measuring physical properties by their correlation with the chemical composition. And that's an extrapolation that's relying on correlations. And those sorts of things are likely to work best. I think the slides lost a bit off the bottom, or at least my version has. They're likely to work best when they're used on single species. So if you want a correlation to hold up, a correlation between the amount of lignin and the strength, for example, then it's much more likely to hold within species than across. And of course, the challenge is to get multi-species calibrations, because they're going to be much more useful. But I think that's sort of an open question at the moment. I think there is a bit in the literature, but not a whole lot. So a tiny bit about some specific applications. Online NIR measurements have been used to control the moisture content of paper in paper mills for decades. I remember seeing people standing up and talking about that back in the early 80s, for sure. And that's because it's very easy to measure water. Paper's pretty thin at the point where you measure it, so you can see the whole paper, and you can build very cheap instruments because you only need a couple of wavelengths to do that. And that's been used with, I remember seeing videos of really impressive instruments that sort of slid across the enormous roll of paper that was going past at tremendous speeds and were controlling moisture content, which is really high, which is really important for the production. And I've also seen papers where people have looked at sawn timber in timber mills to get at least a rough idea of the average moisture content. Now, you're only measuring a few millimeters, so you're relying there on that being predictive of the overall moisture content. But in a particular situation, that might be good, and it certainly might be as good as a capacitance meter used on the surface of the wood, because that's not going to see very far in either. Density, there are calibrations out there. They're probably not working directly. They're probably working correlations with the chemical composition, and similarly mechanical properties, obviously very important, really useful to get calibrations, probably relying on secondary correlations, and almost entirely, I would guess. And so I think the challenge here would be get something that works across different species, although maybe that's not important. If you can use the NIR spectra to discriminate between species, then you can switch to a species-specific calibration. So that would be another way to do it, and might work really quite well. And the user needn't know that. It can all be in the software. You can point it at a piece of wood, and it can determine maybe what the wood is, and then switch to a mechanical property calibration for that type of wood, and use the chemical composition there to do that. So there are lots of possibilities. From my quick looking through the literature last week, lots of these are still possibilities. There's scope for loads and loads of research, and maybe some of you guys will be involved in that. So I will leave you. I'm happy to take questions. I'll leave you with a few references, so that some of what I've been saying about the wood's been taken from a really nice review by Satoru Tsuchikawa from Japan, from Nagoya, and there's a load of references in a couple of special issues of Journal of Near-Infrared Spectroscopy. So thanks for listening. Happy to take questions.
Thank you so much, sir. This was a very, very interesting talk, and I loved learning about its applications. And I have a question for you, but before that, I can see there's a question from one of our viewers, and the question is: can NIR spectroscopy be used in agriculture industry to non-invasively judge the ripeness and other parameters of the crops?
Yes, for sure. It's being used. There are quite a lot of applications in fruit. So you want to harvest fruit when the sugar content's right, and you can measure sugar content with NIR. You can do it to some extent with NIR on intact fruits, although clearly you've got the problem again that you're not going very deep in, but there's correlation between the surface and the depth. And so people are certainly working on, and I think using portable NIR instruments to measure the sugar content in fruit while it's still on the tree, while it's still on the plant, and decide when to harvest. And I think similar applications are being used on grapes. And people are using NIR to measure crops in the field, for example, using a drone, flying a drone over the crop, and you can measure the protein status of the crop, for example, and decide whether it needs more fertilizer on. You can measure the moisture in it. People are using similar applications to look at to detect weeds, so to detect things that shouldn't be there in the field. So lots of applications, and the applications flown over fields in drones are really interesting.
Thank you, sir. Sir, since you said that IR cannot go very deep into the sample that we are testing, and from a few other documentaries that I've seen that they also have some characteristic that can be seen using ultraviolet cameras. So why do we not have ultraviolet spectroscopy of the things that you talked about?
You do. So quite a few of the NIR instruments will also measure in the visible range as well, and so you see visible NIR calibrations using both of those, and clearly there's a lot of ultraviolet spectroscopy goes on as well, and people. So by the time you get into the ultraviolet, what you're not seeing is vibrational spectroscopy. It's other sorts of things, but yeah, I mean. There's scope for using the whole of the electromagnetic range. I mean, obviously it gets a bit more difficult when you're using something like X-rays, because then there are all sorts of health hazards. But you can use the whole of the range, and you can combine different ranges. It might mean having two instruments essentially, and combining the information from multiple sensors. But again, as the sensors become cheaper, and as the computational technology gets more and more powerful, there's scope for doing that. Yeah, and NIR isn't the answer to everything, and one shouldn't decide in advance, this is how I'm going to measure it. You should think about the problem, and you should decide what's the best area to measure, and maybe it's more than one region.
So can this be expanded in the view that we can also find out the diseases that are present in the plants?
Possibly. It will be secondary. So one of the things that's true about NIR is that it measures percentages rather than parts per million. So if somebody shows you an NIR calibration that's claiming to be measuring parts per million of something in something, either they're using a secondary correlation with something they can measure, or they're cheating, because you cannot directly measure things that are only there in tiny quantities. So you can't measure virus in a plant, for example. But what you can possibly measure is the symptoms in the plant of that virus. So, or if you've got a fungal infection, you won't. What you may measure is the damage to the plant due to that fungal infection, and that certainly people have done. And so one of the things people have been interested in doing there is measuring aflatoxins in peanuts. So that's a really serious problem. If peanuts are infected with aflatoxins, then the mold isn't the problem, but the toxins that it produces are deadly. And you can't measure the toxins, but you can measure the fact that the peanuts have gone moldy. The problem with that application is the sampling. So if you've got a lorry load of peanuts and there's a mold growth in a few hundred grams in that lorry load, then the problem is not measuring that. The problem is representing that in your sample. So you could take 20 kilos from the lorry and not see any of the infected stuff. But it's certainly capable of doing those things through indirect measurements.
Thank you, sir. Thank you so much, sir. So I think Ashish sir also has a few questions, sir. So I'll yes.
Thank you, Shantanu. Thank you, Professor Tom. Really, it's a wonderful introductory lecture on NIR and its application on wood science and technology. And most of the question, it's a good thing. And as per your experience, you have covered most of the query related to my NIR application on wood science part. You have covered under the general comments on your slides. Okay, so I would not ask you on the application sides of NIR spectroscopy, but I would like to take your intake, your take on the, because when I've gone through the most of the journals and research papers from the different research groups across the globe, I found the ambiguity, when there is no any standards to find out the actual measurement, which kind of a modules we can prefer for the future applications, because somewhere the lot of the pre-treatments we have, lot of the criterias to evaluate the models, so what's your take on that? Can we can we give a solution, especially either it is in a agriculture side or either in a forestry or science? What should be the good parameters to standardize any model? Then you can say, now these are the parameters on the basis of which we can apply it for a future applications or for the future endeavors of in any field. what should be the standards measurement, because somewhere we characterize the models on the basis of ratio performance deviation. Sometimes we can say that the rank should be this one. Sometimes we can say now if the difference between the cross validation and the cross test validation should be minimized, then you can now this is the perfect model for screening. But when this is all these models which suggest us that is only for the screening purpose, especially when we look at the application part of the NIR spectroscopy in wood science and technology. But none of the models told us that now this is the exact model by which we can predict these things in the particular site.
Okay, so I think there are a lot of questions in there. So
Yeah.
I think one partial answer is that I don't think there is a correct model. My experience of applications is that either it doesn't work or it does work. I mean, obviously there's some gray area in between where it sort of half works, but most of them either do or don't work. And if they do work, then lots of different ways of treating the data, finding an algorithm will all work nearly as well as each other, and there's not a lot of difference. I mean, one of the things that annoys me about the literature sometimes is that you see a lot of literature of people taking their fancy new calibration algorithm, comparing it with partial least squares, discovering that it works a tiny bit better, possibly because they've put a lot more effort into optimizing it, and then claiming that this is what everybody should be using because it's much better. And when you look at the differences, they've got no practical importance at all. They're just tiny differences. So I think part of the answer is most of the time, a standard pre-treatment and partial least squares will actually give you something that it's going to be quite hard to beat. So in fact, one of the frustrations for people like me who do actually try to look for new algorithms and look for new methods is that it is really quite hard to beat PLS. So you work very hard on something and you come up with this new method and it looks really good, and then you're on PLS on the same data and it's maybe slightly worse, but really not so much you should be jumping up and down and saying I've got something better. I think the other part of the question, which essentially is about how you evaluate calibrations. For me, the real evaluation is the root mean squared error of prediction on an independent test set. And there's no absolute standard for what that needs to be. So if you're thinking of replacing some standard method for measuring protein, for example, then it's got to be competitive with that. If you're maybe developing something, a new application that you know isn't going to work brilliantly well, but might be really useful for screening and really better than nothing at all, even if it's not working terribly well, then you might accept something that's a lot worse. So for me, it's performance as judged by mean squared error prediction on a separate test set, and comparing that level of performance with what's of any use. Can I use this? Is it worth having? And the answer, I mean, the level at which it will be worth having will vary tremendously with the application.
Yes, Professor Tom. Actually, really, when I was in early days of my research, really that time is very tough for me that which model I have to use or not. And really, it's a continuous pattern to you can optimize the models, and day by day you just learn for the betterment to standardize the model. Really, I fully agreed with your view on model optimizations. Now, Shantanu, now time is not
Ashish, I
allowing
think there's
us
one
to.
last question, sir. There's
Yeah,
one
sure,
last
sure.
question, sir. The question is, what should be the sample size when we want to distinguish two or more lookalike wood species?
The sample size, I guess my answer to that is it's sort of the wrong question. The question should, when you're doing discrimination like that, classification, the important thing is to represent all the natural variation in each of the classes. So what you don't do is just take lots of replicates of very similar samples. So the stuff in the literature, I think the worst paper I've seen, and I forget who wrote it, was somebody who was claiming to be able to distinguish different types of bottled water. So they can, different brands of bottled water. And the experimental design was to go around to the supermarket, buy off the same shelf 3 bottles of brand X, 3 bottles of brand Y, 3 bottles of brand Z, and you bring them back to the lab and you take spectra from each of them, and lo and behold, you can distinguish the brands. But if you try to distinguish the 3 bottles of brand X from 3 bottles from a different supermarket, from a different batch, you might be able to do that as well. So I think the point is, if you're trying to distinguish species, then you need to think about what's the natural variation within each of those species, and you need to represent that in your sample set. And by the time you've done that, you've got enough samples.
Yes, I'm fully agree with the Tom Farm. And dear Shantanu, in the case of wood, it's a very anisotropic material, and even we cannot control the sample size very easily. It's a very tough job in the case of wood science when we are optimizing model for the wood properties, especially because in the radial size and tangential side and longitudinal size, different properties having wood. So we cannot control we cannot govern the sample size selections. Especially, it's a continuous pattern that we can add more samples if you want to robust model. Yes, Professor
you.
Tom, I'm right.
Yes, absolutely. Yes.
Thank you, sir.
Thank you
It's
so
a
much. I think that
wonderful
answers the
session with
question
you.
very well.
Okay.
Okay.
Yes, Ashish.
Yes,
Sir.
Santanu. Yes, sir. Santanu, now I have done. And now I think
Okay, so
time.
I think we do
So,
not have any questions from the audience either. So thank you so much, sir, for the wonderful session and answering the questions so wonderfully and finding the time for this lecture. Sir. Thank you so
So
much, sir.
thank you very much
and
for inviting me. It's been
And
my pleasure.
Shantanu, at last but not least, I would like to thank Storm Fern and our audience as well. And it's my special request on behalf of Dolphin Institute. Please, sir, if time allow you and the situation of allow us in near future, definitely visit India once, okay? And definitely we would love to welcome you at our institute
Okay,
in
thank
near
you very
future.
much. It will have to wait until travel calms down a bit.
Okay, thank you, sir.
Okay.
Thank you so much, sir. Thank you, everyone, for attending the session. We'll see you in the next lecture. Thank you.
Thank you. Bye.
Yes, sir.